if you want to share your screen. Exactly. Perfect.
Yep. Awesome. I hope this is visible.
Great.
Okay, yeah. Yeah, let me know whenever I can get started and I will.
Perfect. Okay, I will start introducing you now. So, hello everyone. Thanks for joining us today. Today we are glad to host Nived. Nived is currently a postdoctoral researcher at Microsoft Research, New York. He recently finished his PhD in Berkeley, and his research interests lie in the intersection between sequential decision making and more recently large language model. Moreover, it has been named a CPAL Rising Star for 2025. Thanks a lot for accepting our invitation. We are really looking forward to your talk. The stage is yours. Thank you.
Awesome. Thanks a lot, Luca. Thanks for the nice introduction and also for the invite. So today I'm going to talk about this joint work with an amazing group of collaborators, Yanjan, Jiantao, and Kanan, the latter two being my advisors. And this talk is going to be about, uh, I guess, this problem called nonlinear ridge bandits. And I'll try to tell you why this problem is interesting, hopefully, and convince you that this is a nice problem to think about, hopefully by the end of this talk. So stay tuned. Okay, so I'll just jump into the setting, and I also just wanted to say if there's any questions or anything of that sort, feel free to just pause me or stop me and then ask your question and interrupt me at any point. I think I have too many slides, so I may not be able to get through all of them, and that's probably okay because as long as I can convey most of the stuff, I'm happy. Okay, so the general setting is I'll just set up some notation before I actually introduce something about this problem. So let's just say the action space of this bandit problem is A. It's not a contextual bandit problem. It's just a simple bandit problem. And there's a class of reward functions, which is like script f, which is parameterized by some theta. And we're talking about bandit problems over a horizon T. And as we all, especially here, very well know, this is a stochastic bandit environment. So the nature chooses this unknown theta star, and this induces an unknown reward function, and the learner interacts with the environment sequentially and plays actions in this environment and observes these random rewards, and hopefully is able to learn something about the unknown reward function. The objective is to minimize the pseudo regret, which is defined as the gap between the total reward that the actions of the learner collected and the best in hindsight action that the learner could have played. And so this is a quantity that's always going to scale with t. And so the focus of this talk is going to be on ridge bandits, and this is called ridge bandits because essentially there's a ridge function, and so the next few slides I'm going to give you an example of what this would look like. And so a classic example of this is linear bandits, and this is has a very a long history, and a lot of cool results are known for linear bandits. So the sort of setting over here is of one where the reward function is nonlinear, but it's nonlinear in a specific way where it's of the form of a link function, which is a scalar function being applied to theta inner product A. So over here, the scalar function is the cubic function, and this is always going to be applied on the scalar, which is the correlation of an action with theta, or here theta star. Okay, so I'm going to jump to the chase a little bit and show you a plot, which kind of is basically what we would like to characterize. And I'm going to do this specifically for this particular link function, the cubic link function. And I just want to point out the scaling is in such a way that theta is on the surface of the unit sphere. So theta inner product A is going to be a number which is at most 1, and the best possible reward you could achieve is just by playing the action theta, in which case your reward that you collect would be equal to 1. Okay, so let's jump to the chase. What happens when you try to plot the min-max regret? And let's come back later to how we actually arrive at this bound. So it turns out there's a curious phenomena that happens. And I'm going to plot two different curves. The first one is linear in t, the second one is d square root t. And so what you'll see is there's a sort of a switch time, and for this particular like reward function that happens to be at t equal to d cube. And so up until this point, the regret scales linearly. And then there is a certain another point which is at t equal to d to the 4, where you see that the regret actually starts scaling as d square root t, and sort of the problem resembles like what a linear bandit problem would entail. And in between, there's sort of like some sort of like some behavior, and I'm just plotting that as being roughly flat. There's obviously going to be some scale in the regret, but it's going to be basically only an increase by a constant factor, essentially, or like some polylogarithmic factors. Okay. And so like you can plot the min-max regret for this problem, and it has this interesting structure, which is like d cubed plus d square root t. So there's some sort of like burn-in time, which is like, you can think about this as the complexity or the cost of like finding a good initial action. And so what I mean by this initial action, I'll come to later, but for the purpose of this slide, you should just think about this as being like some action that maybe has like a constant correlation with theta star, the unknown theta star. And so like in the burn-in phase, you spend some time finding this action. And the learning phase is basically what comes subsequently, where the regret actually becomes sublinear. And given this initial like sort of initial good action, the problem starts resembling a linear bandit. And like you should think about this as how the way this link function looks like around the point 1, or closer to 1. The derivatives are kind of bounded, and so you see that the problem sort of looks like a linear bandit, or a generalized linear bandit for that matter. Okay. So given this interesting phenomena, basically I'm going to work backwards to try to motivate what the questions are for this talk. So first of all, why does this phase transition even occur? And like, when does the regret turn out to be sublinear? And the question will be, what happens more generally across different link functions? And how does the burn-in cost and sort of like the initial cost that you spend, the d cube in the previous example, actually depend on the structure of this link function? And obviously, along the way to answering these two questions is also what are algorithms which actually achieve these burns? So the plan for this talk will be to I will set up the problem a little bit more formally, and then talk about two different upper bounds. So the first one is like a sort of general upper bound that works for a class of link functions subject to some assumptions that I'm going to introduce to you soon. And then the second half, I'm going to talk about what happens when you run a very natural algorithm like stochastic gradient descent. And we'll consider a particular variant of it, which is called interactive SGD, where the interactiveness comes from just from the fact that this is a bandit problem. So you can be clever about how you choose which actions to query, like the rewards at. And then I'll talk about some some like lower bounds and some techniques that we've developed to like arrive at some like min-max lower bounds for this problem. And then finally some implications and extensions, which I think is like maybe the most interesting part of this talk, and like connections with a lot of existing work. Okay, so going back again, like the setting is this nonlinear rich bandit problem. So I'm going to focus on the case where the parameter space is like basically the L2 ball. Or I should not say the L2 ball, it's the surface of the L2 sphere. So theta has L2 norm equal to 1. And the action space is also here is the L2 ball. So these are all the actions, like all the vectors which have L2 norm at most 1. And the reward function has this structure which is like a ridge function, or you can also call this a single index model, depending on which area you're from. And so there's a known link function f, which is applied on sort of like the correlation of a and theta. And the assumptions that are going to be core to this talk are, I'm going to assume that f is such that the scale of this function is normalized. So f of 0 is 0 and f of 1 is equal to 1. And you can always rescale your function, or like in case your function does not satisfy this property, you can rescale the bounds in such a way that you kind of arrive at something for your choice of f. More critically is like this assumption of monotonicity, which is here, basically you should think about this as like f is, let's say, increasing on the interval 0, 1 and even, or it's increasing on -1, 1. And so this is saying that somehow like the parameter recovery problem, which is like of recovering theta star, and also the problem of minimizing your regret are kind of like synonymous with each other, basically, because if the function is increasing on this interval, then recovering outputting your action as being theta star is the action that actually minimizes your regret. Um, okay. And finally, I think this is an assumption that is like satisfied by many link functions of interest, including the cubic example that I told you, and in general, like many polynomials, and like the softmax function, for example, which is the function is like locally linear near one. And so all this means is that here you should think about point one as just being like any constant. And so this is just saying that the ratio of the maximum and minimum derivative of the function around some region around the point one, which is like the maximum, like the maximizer of this function is like it's upper bounded by a constant. So what this is saying is like in some local region of one, the function looks kind of like a generalized linear function. Okay. Yeah, I'm going to pause for a second just to ask if there's any
So,
questions about the setting itself.
yeah, Oda, go ahead.
Oh,
Okay.
yeah, I just
Yeah.
had a quick question. Maybe I missed
Mhm.
this part, but like, what is the importance of being locally linear around one?
Oh, good. So I think this assumption is motivated from specific cases of f that like we were inspired by to come up with this problem, and like all the polynomials, like x to the p, for instance, are like functions that sort of satisfy this property. Um, Yeah, and I think maybe another way of looking at this is uh, what is even the role of the derivative of the function? Like, what is the meaning of this quantity? And I think hopefully over the next few slides, like, it'll be clear like why the derivative is like a measure of sort of like the SNR effectively that you see for your problem. So here, this is just saying that like maybe a lot of the hardness of the problem is before you get to this regime, which is like local around one, because initially like you're playing random actions, and so the correlation with theta star is going to be like 1 over square root t, which is very far away from this regime, and so you have to improve your correlation till that point. And all this assumption is saying is beyond that, like the problem looks like a a linear bandit problem effectively.
Okay. Yeah, I was gonna ask about the F prime, but I think you'll explain it, so
Yeah,
that's
you'll see
yeah.
that in a few slides.
Okay, sounds good, thanks.
Okay, so literature review, and like maybe I'll try to convince you that, and it's also sort of clear that this problem at least models linear bandits, but there are many examples of functions that people have studied in the literature that kind of capture either special cases of or generalizations of the rich bandit problem that I described. And so, yeah, the linear bandit is of course like a very classic example where we know that the optimal regret scales as d square root t. And the same sort of behavior applies when you study the generalized linear bandit setting. So the derivative of the function is bounded above and below by constants. Uh, and so yeah, you can also study the case where f is concave, and this yet again has the same behavior as linear bandits. And then you can go to the case where f is like nonlinear, and maybe concavity is already an example that satisfies that, and GLMs as well. But yeah, the function, let's say f of x is x squared, and it turns out yet again that you see the same regret scaling. And then, maybe one more generalization is the polynomial case. And here you see that the optimal regret actually depends on p right now. So when p is equal to 2, or I guess here p is greater than equal to 2, but yeah, beyond p equal to 2, you see that there's like some worsening of the regret. And yeah, here the parameter space, just to be clear, is like the entire unit ball. So it contains the interior of the ball as well. Okay, yeah. And so there are also some like general complexity measures for bandits, such as the DEC and also the information ratio. Like these are two general quantities that you can compute for your bandit problem to determine sort of like some upper bounds on the upper and lower bounds on the sample complexity of the problem. Um, Oftentimes, they do not lead to tight regret dependence on D. while they'll say something that's polynomial in D, maybe the exact dependency on D may be off. And so this is something I will like come back to at the end of this talk to like address whether this happens for this particular problem or not. Okay, yeah. So yeah, part one of this talk is going to be the main results. So yeah, just to be clear, I'm going to ignore like logarithmic factors everywhere. Okay, so I guess the main result from our work is sort of like regret upper and lower bounds. And so the main upper bound that we establish is assuming that the function, like the link function, is monotone and it has local linearity. There exists an algorithm achieving the following regret bound. So it's composed of two parts. Yeah. So I guess the first term, d squared, this is like an integral expression. And the second part is d square root t. So the first term is like does not really have any t dependency per se. So this is like a sort of like the burn-in cost, which I had described earlier for the cubic bandit case. And the second term, the d square root t, is sort of like the scaling that you'd get from the eventual linear regime that you will be in, and so there you kind of pay the regret of a linear bandit problem. And a stronger result is also true, and like where you kind of replace the f prime of x by the maximum derivative of the function between 1 over square root t and x. And so I guess maybe again the same question arises, like where is f prime coming from, or what does this kind of have a role to play exactly in? And this will turn out to be a natural model of the SNR. And I think the best way to actually show this is through an algorithm that like works for this problem. And in fact, both the algorithms for this that I'll talk to you today will kind of naturally, like this f prime of x as being some measure of the SNR of the problem will naturally pop out. And so this is just saying, yeah, you can kind of get something slightly stronger. And so, yeah, like I said, the first term is the burn-in period for the problem. And the second thing is kind of like the learning phase where the regret is actually sublinear. Yeah, so the sort of interpretation of the burn-in period you should think about as, the ultimate goal of this phase is to like come up with an action that has constant correlation. So here I picked that as being a half, and you can like replace this with any constant that is larger than kind of like that falls within the locally linear regime, or is at least bounded within that region. And so like the integrand x sort of captures the current progress of the learner towards finding such an action. So initially you're playing random actions and your progress starts around 1 over square root d. And like over the course of the algorithm, you kind of improve, and you eventually get to sort of like x equal to a half, and then finally you get into the learning phase where the regret is d square root t. Okay, there's also a lower bound that we establish, and this is maybe at some like surface level looks very similar, but they are two different expressions. And so basically what we can show is a lower bound where f prime of x is replaced by f of x, and the factor d square is replaced by a factor d. So this is a like, lower bound on the sort of like the burn-in term, and it is subtly different. But for many functions that you would care about, including all functions of the form x to the p, these two will coincide with each other. And generally speaking, like for any function where the derivative around the origin is like kind of, or the derivative grows fairly sharply starting from the origin, for these kinds of functions, you should expect that these two bounds will coincide with each other up to polylogarithmic factors. Okay. So yeah, one salient feature of both of these bounds is the burn-in cost actually depends on the entire function f. So it doesn't just depend on it on a single point. It depends on it everywhere. And just to like point this out, I mean, yeah, you can sort of, oh, sorry, yeah. Yeah, so just to point this out, like you can sort of, I'll come back to an example where it will kind of look different for two different functions which look similar to each other in some which way. Yep. So we also have some results on like a learning trajectory in the burn-in phase. And so yeah, here you should think about sort of like two curves that you can plot. And so the upper bound is like, this is defined by the following differential equation. And there's another curve, which I call the lower bound curve, which again corresponds to a different differential equation. And the result that you can establish is there is an algorithm who's like, just to be clear, the x-axis is time and the y-axis is the correlation of the actions of the learner with theta star. And so there is an algorithm that kind of lies above the upper bound curve at every point in terms of the correlation that it achieves with theta star. And at the same time, for every algorithm, there is sort of like an instance under which its correlation with theta star has to be below this the blue lower bound curve. So maybe the notation is a bit confusing because I'm saying something that you're above the upper bound curve, but you should just think about this as induced by an upper bound algorithm, effectively. Okay. Okay, so I'll just talk about like a few examples. So polynomial bandit. And so for this case, like you can actually compute the quantities that I told you earlier, and it'll turn out that the fixed cost essentially scales as d to the p. And so this this appearing as a fixed cost has to do with the way we kind of set up the problem to begin with. And so you can also like compute this like for this bandit problem, compute what let's say eluder UCB and information directed sampling the upper bounds would give you, and those would scale slightly suboptimally as d to the p plus 1. So this is just a deficiency with the analysis maybe at this level, more so than about the algorithm itself. Yeah, and another point is somehow like the previous bound tells you that f is important at every point. So if I tell you that the function kind of in the first case just grows quadratically, the fixed cost happens to just be d squared. But if you change the function slightly to add this like flat region in the middle, so maybe you should think about the first the first increasing part as being of length like order 1 over square root d, and then there's a flat region beyond that. Somehow the fixed cost of learning, or like the burn-in cost, it shoots up to like d cubed. So yeah, like this just shows to you the importance of the behavior of the, or like sort of the derivatives of the function at every single point. Okay, yeah, so sorry, was there a question?
Yeah, I was going to ask, when you say every single point, back in your integrals, did your integrals not start at sort of 1 over square root d? So can you actually
Yeah, that's right.
ignore
Okay,
the
so
first square root d? The first 1 over square root d?
Yeah, it starts at 1 over square root d because I guess the intuition is just that like if you wanted to, let's say, come up with a lower bound, then you can't have something that actually depends on something that has a depends on the behavior of the function on a smaller interval than that, because a random action would always like get you something which is like 1 over square root d. So your regret may not be meaningful at scales of the function which is even smaller than that. But yeah, so when I say importance of the function at every point, I mean like on most points.
Okay.
Yeah. Okay. Okay. Yeah, I will jump into like some sort of like understanding of how do you arrive at these upper bounds, and also hopefully, yeah, like some things will be more clear about why f prime shows up in any of these bounds and why we have to make any assumptions about it. Okay, so I guess the learning phase maybe is the easier one. So let me just jump in over there. So like, let's assume that you have an action that kind of has like constant correlation with theta star. Then the learning problem effectively just devolves to a generalized linear bandit problem. So you don't have to, worry too much about what, like you can kind of like use an existing algorithm just to like solve the problem in this regime. And so maybe how I will say this is like, you can kind of argue that even something as simple as a version of like explore then commit also works for the problem at the scale. Right. Yeah. So yeah, in the linear regime, you kind of have not really too much of a problem. The hard part comes where, like, let's say in this case, f of x is equal to x cubed. The behavior of the function around the origin, where the derivative kind of vanishes, and the fact that the derivative vanishes is like probably testament to the fact that like if you kind of move along the x-axis, the y-axis does not change. So it's really hard for you to know as a learner whether your correlation with theta star is improving or not. Like playing random actions, and like it's kind of hard to certify that you're actually improving. And the function is giving you very little feedback about this because and this like feedback is kind of buried in Gaussian noise. So it's harder for you to know whether you're making any progress or not. And so that's sort of why like the learning problem becomes harder. In this case, like around the origin where the derivatives are vanishing. Okay, yeah. So I guess, yeah, the part that I'm going to talk about now is like what happens in the burn-in phase where you're in the initial period where the derivative of the function could potentially be small or it could change in many different ways. And so the target, let me remind you in this phase, is to like find an action that has constant correlation with theta star. So the algorithmic primitive, this is based on some ideas of Latimer et al. And so you kind of like imagine that your goal is to just find a bunch of actions that are all orthogonal to each other. So A1 through, let's say, A d over 2. I'm just picking d over 2 arbitrarily. And the goal that you would like is for each of these actions to have, let's say, correlation 1 over square root d with theta star. And so you kind of resample and then you kind of use a hypothesis test. So a random action will satisfy this property, but you need to certify that this is going to be true because you're doing this d times roughly. And so you need to design a hypothesis test that will certify that this is true. And then finally, if you imagine that you found that your hypothesis test succeeds like order d times, and you just look at the sort of action A1, like the sort. So this is like a weighted linear combination of all the AIs. And because the AIs are all orthogonal to each other, this is also a vector which lies in the action space. And you can compute, it's like a one-line calculation to take the correlation of this quantity with theta star and see that the correlation is going to be a constant, essentially. So yeah, like so like computing this, solving this problem is equivalent to like finding these d orthogonal actions, which have good correlation. Was there a question?
Yes. So are you requiring that every action has at least this correlation or just the final one, AT?
No, every single one. So yeah, I guess maybe here I should have been clear. Like for every, this is going to be run for t equal to 1 through d. And for each one of these values of t, you want the correlation to be 1 over square root t.
Right. So essentially, we're going to sample a batch of orthogonal data, and we'll keep resampling it until the entire batch has a positive at least 1 over square root d correlation with theta star.
So that's maybe one way of thinking about this. But if you really want to be efficient, you should just think about this as like you're doing this one at a time. So you sample your first vector, and then maybe you run a hypothesis test to certify that this is correct. And then given this vector, maybe you can do something slightly more clever to figure out the second vector and the third vector and so on. Right. But ultimately, your goal is to like have this sequence of d vectors. And the question is like, how do you really do this? Which is what I'll talk about next.
Perfect. Thank you.
Okay, so now let's jump into some math, which is like what does this hypothesis test subroutine look like? Okay, so let's imagine that you have like an action. Let's call this aref. This is some reference action. We'll come back to what this actually means a little bit later. But let's say you have an action which like has correlation equal to x with theta star, and let's imagine that you're drawing your newest vector at, and this here is denoted v basically, and you want to certify that this is this has correlation at least 1 over square root d. So what you can do is you can just like compute given aref and you've sampled this v and you want to check whether it is at least 1 over square root d or not. If you look at the difference of theta star inner product aref plus v and theta star inner product aref, the difference of this is like f of x plus 1 over square root d minus f of x. And you again, like if you think about 1 over square root d as being kind of small, this is really like the derivative of the function at x times 1 over square root d. So the derivative of the function being larger, it sort of like gives you a bigger gap over here in like what you're looking for. And in case the action was not bigger than 1 over square root d, maybe the gap between these two quantities is not going to be as big. And so what you do is you get random like sort of observations. And what I mean by random observations is you query the action aref plus v and you query the action aref and you get two observations and you can take the difference and like solve a hypothesis testing problem basically. Is like, which is like, does it satisfy this hypothesis or not? That's the null hypothesis. And to test this, you're going to basically need like 1 over gap squared, which is like d over f prime of x squared samples to test. Okay, good. So this assumes that you have like this action that has like basically it has some reference inner product, but by virtue of having found this vector v that has like a constant correlation with theta star, and you should think about aref here as being like maybe the weighted linear combination of the ATs that you have computed so far. So this has some correlation, but and like basically like having found such a v which satisfies this property, you can compute a prime ref, and a prime ref is just going to be like a ref plus v effectively with some scaling in there. And this actually has better correlation now. It's like x plus 1, like square root of x plus 1 over d correlation. So just to be clear, like the previous subroutine that I said is kind of like trying to find whether you're improving or not by like looking at the behavior of how the y-axis changes by adding the vector v to theta star plus aref, and in terms of the observations that you make. And once you've computed such a, like found such a v, you have a new action that like kind of moves you along the x-axis a little bit more. And if you really think about the function as like having growing derivatives, so maybe f of x is equal to x squared or x cubed or any of these functions where the derivative improves, you actually see that like now you're at a point where solving the same hypothesis testing problem is just a little bit easier because the derivative has like increased a little bit from the first point to the second point. And so you kind of like need slightly fewer samples to test. And so I'll just add that, if it just so happens that like the derivative is not like here, I chose this reference point because the derivative here was maximum at this point. But if let's say the function had slightly different behavior where the derivative was like larger somewhere before, you can always like move back and like solve the same testing problem around a different point, which is like earlier on in the space. Okay. And so like this sort of is the core subroutine. And once you have this, like you can kind of iteratively peel off one of the ATs at a time. So every single time you kind of compute A1 and you compute A2, and like at some point you have a set of AIs that you've computed. And the next one that you compute, you use the existing ATs that you've already collected so far to define a reference action. And this is like maybe has like this is a point which kind of has reasonably good derivative, better than doing the same testing problem around the origin. And so that sort of like makes your life a little bit easier. And so this is like kind of important because it lets you use the adaptivity of this problem a little bit more strongly. Because if I just said aref is equal to being 0 every time, then you're effectively just solving like you're not really using the structure of the problem, or you're not using any adaptivity of the problem at all. You're always querying random actions at that point.
Sorry, Nived. I think there are some questions.
Okay. Yeah.
Go ahead if you want.
Yeah, I was going to ask, how does this, so how do you change a ref to pick a point with maximum derivative? Because everything you've described so far makes perfect sense, but I didn't quite catch the part about how you might move back to exploit a point with
good point.
high derivative. Would you need to sort of have already figured out the function closer to 0, or?
Right. So the setting that I'm telling you about, the link function is like perfectly known to you. So you know the behavior of f at every point. And
Right.
what you have is a reference action. And maybe all you can certify is like the reference action has correlation with theta star, at least something. Maybe you can say that it's between, let's say, I don't know, like let's just say like 1 over like 100 over square root d and 200 over square root d. Like you have some bounds on how good this reference action is at the current point. And maybe all this should be interpreted as is like you can kind of move to like you can kind of scale down your action if it just so happens that the derivative around like a different point in the same interval is like smaller, basically. I don't know if I answered your question very well,
Perfect.
but
Yes, that completely answers my question.
okay.
You know the link
Yeah.
function, the actions are on in the ball and not on the sphere.
Yes.
So you can always scale down your action if you want to get if you want to move back to a point where you have a better gradient.
Yeah, exactly. That's perfectly correct. Yeah. So that's like the action space being the ball makes your life a little bit easier in that regard. Yep. Great. Okay.
I have another question, maybe.
Oh, yeah.
How do you ensure that the ARF plus V remains in the ball? So the V,
Great question. So here you should just think about this as I'm gonna I was being a little bit callous when I wrote this. Like you should just think about scaling everything maybe by 1 over root 2 or something. So ARF plus V over root 2, which is like going to be in the ball, and also ARF over square root 2. So like you're still looking for maybe here like maybe or you should just think about like maybe 0.99 times all of this over here. So like everywhere the derivative that you compute may be not around x but like 0.99 times x, like something morally very close to the current best point that you have, or like the current reference point that you have. So you can kind of scale this action down by just a little bit because like ARF and V are going to be orthogonal to each other basically.
thanks.
Can I also ask a question?
Yes.
Yeah. So far, from what I understand, and maybe you're going to touch upon this in a little bit. So some of these barriers seem to be information theoretic, but are you going to also talk about computational barriers? So maybe you have enough samples to get to a solution, but you can't actually get to the solution. Is that?
So okay, I think for most of the sort of settings that you would encounter here for different choices of f, basically, I don't think there is a separation like a computational statistical gap, just because yeah, like the structures of these functions are kind of okay. Let me take it back. I think you're right. So there should be like many cases where we do see a gap, I think, depending on the structure of f, and that won't be the focus of this talk. So yeah, like you should think about f as being something simple as like a polynomial or something like that for this setting.
Got it. Thanks.
Yep. Okay. Yeah. So if there's no more questions, I'll move to part 2, and let me just check how much I'm doing on time. Okay. Yeah. Okay. So I guess one thing about this like upper bound that I just told you about is there's like two distinct phases where you have a burn-in phase, and then you use like two different algorithms basically across the two different phases. And so you can ask like what happens when you like try to implement a very natural algorithm, and SGD is one that comes to mind. And so yeah, I guess the second part of the talk I'm going to focus on is like a unified algorithm via sort of like an interactive version of SGD that uses the fact that this is like like an interactive problem. Okay, so like the vanilla SGD on quadratic laws, you can think about this as being okay. So like here, the gradient is with respect to the quadratic laws, and so every time you like update your parameter theta t in such a way, and I'm just being a little bit careful here to compute the spherical gradient. So you're like always renormalizing the sort of vector that you've like the new parameter that you've come up with back to the surface of the sphere. And here like this is like sort of in the IID setting essentially. So all the observations that you have like ATs and these are all like Gaussian observations. And so yeah, like this is a very natural algorithm, and there's a very long history of work that analyzes this algorithm in the setting with Gaussian measurements. And it's well known now that there is a quantity called the information exponent that kind of captures like the sort of sample complexity of this problem. And this is a very natural algorithm, but there's something more about the Bandit framework that we don't use here, which is the fact that you get to choose what ATs you get to pick. And so maybe you can come up with an algorithm that works better in this particular framework. So what I'm going to talk about briefly is like a simple modification which adds exploration. And so here, and this is what I call interactive SGD. So the update is exactly the same except for how you pick your actions. And previously, you should just, if you just imagine that you didn't have the first term and the sigma t at all, you're basically playing AT is equal to ZT, where ZT is just a uniformly random action on the whole sphere. And now what you're playing is like a weighted linear combination between the current parameter theta t. So this is like a sort of a point on the surface of the sphere, and a zt, which is like orthogonal to the it's basically sampled orthogonally to the current theta t that you're at. So just for like a picture, there's some unknown theta star, and you have some theta t, and you sample zt orthogonal to this theta t, and you like scale it in a way where so like sigma t sort of captures how much exploration you're doing effectively. So you like scale it depending on sigma t to back to the surface of the sphere, or back to like projected back to the L2 ball basically. Okay, and so yeah, like I said earlier, when sigma t is just 0, like sorry, I should have said sigma t is equal to 1. This is a typo. You go back to the case of Gaussian measurements. Yeah. Okay, yeah. So again, the whole point of this like local exploration is to try to take advantage of this phenomena that I described earlier, which is like the improving SNR as you continue exploring. So let's imagine that you're running SGD or like interactive SGD even for this matter, and you currently have an action that has correlation with theta star is equal to x1. And so like the derivative of the function here is small, but then as you like progress, you see that the derivative improves. And so maybe what you should be doing is like sort of exploring around this point x2. And so the derivative of f improves. And so like maybe this means that gradient descent has like there's like a stronger signal in terms of like the norm of the gradient, or like the magnitude of the gradient itself, for improving and getting closer to theta star. Sorry. Yeah.
So
Any questions? Yeah.
yeah, just to clarify, because this is kept on confusing me. None of your assumptions actually rule out signal to noise ratio getting worse, do they? You could have a concave function which satisfies all your assumptions.
Yes. So good. So for the purpose of what I described in the previous section, the point of adding like scaling down your action in a way where you pick the point where so far the derivative is maximum, essentially, like this mu quantity that I pointed out earlier. This is there to like kind of take advantage of the best derivative that you have so far. And so the bounds that you will write down over there have this like this is okay. Maybe I should just show you the thing instead of saying it in words. Yes. So this expression where you like have the maximum over here actually accounts for cases like that, the one that you just said, where the derivative need not be increasing. It's like possibly it could decrease at a point in the future. And so it turns out you can also be adaptive to that, and you can always like scale it down where you're picking the best derivative effectively. Okay, so that's true over here. But if we go to like SGD, which maybe was what your question was about, you can also try to do the same thing over here, where you like change the sequence of sigma t's that you see. Because like if you imagine that you're setting sigma t equal to 1, then you're exploring around the point 0, and you set sigma t is like any quantity, you're like exploring basically around some region of the around some slice of the function, maybe where the derivative of f is like very, very high. But to actually like implement this program that I told you, you need to have a sense of like how big theta t inner product theta star is, because like this tells you where your reference point is, and then maybe you can move back and forth from that reference point. But because of the way we like implement SGD, you don't really have an exact, maybe you have some crude bounds on it, and it turns out that it's kind of hard to actually come up with a very tight bound, or like a sandwich telling you this is where you're going to be at a given time. And so because it's kind of hard to say that, it's hard to like get this to work without estimating something. Like if you're willing to sit and estimate theta t inner product theta star, you spend a few samples and you do this, then maybe you can get away and do the thing that you just said.
What what would happen if we considered a link function? I believe this is within your set of link functions, which is essentially flat. You don't require symmetry, right? So we could set it so that the highest gradient is near is -1 allowed or is -1 not allowed? Is it
Let's say -1 is allowed. Okay, so
is allowed? Okay,
mhm.
so we're going to set it to be essentially high gradient around -1, the log function shifted back. So you have high gradient on -1, and then essentially flat for all the positive values. So that we almost completely decorrelate the idea of sort of signal or gradient from the idea of high rewards. Does your lower bound still hold, given that it's based on only the gradient of the positive of the large part? And how would these algorithms perform?
Let me see if I understood your question. So basically, like, are you saying something like a ReLU function where you have like a flat region around the origin, and then maybe the derivatives of the function are kind of large as you get closer to 1 or -1 or something like this? Or
No, the
no?
sort of imagine log n. Imagine log n shifted so that the asymptote is near -1. And
Okay.
near 1, we have the flat region. Imagine the extreme version of this log like log n.
Okay, so I see. It's like a function where the derivative is really large, close to -1.
Yeah,
And then like even around 0, the derivative is probably kind
completely
of very
flat.
small. Yeah,
Yeah.
okay. So I think for functions like this, you basically you kind of suffer from the fact that the derivative is small around 0. And I think that's probably going to show up for a function which basically its derivative, if you imagine you're moving along the negative x-axis, its derivative actually grows in magnitude really, really fast, right? So
Yeah.
for functions like this, you'll actually pay a kind of heavy price around, because of the fact that the derivative is very small around the origin. And so you asked me two questions, like what happens to the lower bound and what happens to the algorithms themselves. So the lower bound that I told you actually captures this fact. And so like in general, for like any function where the derivative around 0 is like flat, even like I'm going to take your example as saying like maybe there's like a constant sized interval around the origin and the derivative is like incredibly small within that region, then like somehow the lower bounds will say that the number of samples you need scales is like e to the d or something like that, because you kind of get zero signal until you escape from some region around the origin. And you should always imagine that you're starting at the origin, because you're like theta star inner product a is going to be like 1 over square root d. It's going to be very close to 0 at the beginning. So the lower bounds will scale this way, and then if the lower bounds are like exponential, basically the only thing you can do is brute force search. Like you just throw out a random action, and then you like estimate what f of theta star inner product a is going to be. And like again, just by anti-concentration, you should hope that like at some point you'll hit this constant correlation or something like close enough to -1 in this case, and that'll like be sufficient for you to like actually improve beyond that.
So you don't think there's a chance that setting up SGD? Oh, I guess
I guess it depends on how the function looks like around 0. So well, I guess maybe what was the goal of this question? Was it to ask like what happens if the function actually wants, like the SGD dynamics wants to move towards -1?
Yeah, I was wondering if there are settings in which you might be able to do better by actually forcing exploration in the sense of heading towards negative values rather than towards positive values, and whether there might be, like if I could get a good estimate by suffering a lot of regret by aiming for -1 initially, and then
Right, yeah.
essentially for the remaining time have a near perfect estimate having paid this price.
Yeah, I think you could totally set up a problem where something like this happens. And maybe I will say that like you should not think about SGD in the way I'm presenting it as being like an algorithm that like solves all these cases, because there are many cases where like it is, for instance, you can also show that, let's say the derivative of the function starts out as being linear, and then it's like becomes flat, and then it like again becomes linear. So there's like a region where it's flat. Because the function is linear around the origin, you can actually solve the problem effectively. Like maybe even like sort of IID samples, like basically like uniformly random exploration is like good enough to be able to solve the problem. But if you do like interactive SGD in the way that I told you, like it's going to improve its derivative, and then it'll hit the region where it's kind of flat, and then it just basically gets stuck. Like it has no way of moving past this and like getting out of this phase into the linear part of the function itself. So you could solve that if you like were adaptive with how you change the sigma t schedule. But that's already a case where like maybe SGD is not like at least interactive SGD in the way I presented it to you is not the right algorithm for it. So my belief is like there maybe is like a more general way of like viewing all of these, which also addresses like many of these like useful cases that are not considered like in terms of like what this algorithm can do.
Thanks.
Yep. Okay. So yeah. Okay. So let me just tell you a theorem, and I think it's good that we had this discussion, because I guess like the fact that SGD does not like generically work means that we kind of have to impose some assumptions. Like the example that I just told you about, where the function is flat, but around the origin it's linear, and maybe towards close to 1 it's again linear. This is like an example where SGD just you can prove that it does not work. Yeah, and so like you have to impose some assumptions, and if you assume that the function f is convex, so I'll talk about like two special cases, and then try to tell you like why these are also like kind of interesting special cases. So yeah, one of these is like f is convex. And so you can kind of show that SGD, like again, maybe there's like some mild condition on the initialization being like not too close to 0, just because if you want to recover like exactly the right bounds. Yeah, in that case, like under the same assumption, like monotonicity and local linearity, you can arrive at the exact same regret upper bound that I showed you in the very first few slides about the general case. And so there's some choices to be made for implementing SGD, which is what's the sigma t schedule and what's the learning rate schedule, which I guess I didn't mention earlier, but there is also a learning rate in the algorithm, and you have to decide how to choose it. And so yeah, like the exploration schedule, which is the sigma t schedule, will turn out to be in the initial burn-in period, you pick this to be a constant, and then once you're in the learning phase, like once you so this does require like a test to determine whether you're in the learning phase or not. And once you do that, you kind of temper your or you can kind of also do this by just waiting for like running this algorithm for a sufficient amount of time, which is like basically for this time, like the burn-in period amount of time. And then as soon as you've like run it for this amount of time, you don't do any estimation. You just switch to like the second learning rate schedule, which is d over square root t. So this is like kind of like you're now tempering the learning rate schedule. You're going to decrease it. Oh, sorry, I meant to say the sigma t schedule. I should not be calling this learning rate. The exploration schedule gets tempered, and you intuitively you need to do this because like as you get closer to 1, you don't want to pay linear regret anymore. So you kind of have to play actions that are like very close to theta t, the theta t that you currently have. And so like picking it as like d over square root t turns out to have the right scale to get the regret bound to work. And also, yeah, like I said, there's a learning rate schedule, and yeah, I guess for the case where f is convex, in the burn-in period to come up with this bound, which is like looks slightly complicated, it does require like a bit of care in choosing the learning rate. So there's like an epoch-wise way in which you choose it, where in every epoch you should imagine that like the SGD iterate improves its correlation from like square root I over d to square root I plus 1 over d. Or it's you know that it's at least this much. It could be much bigger than this too, potentially, in which case maybe you don't have to even write this statement down. But yeah, you can argue that in every epoch, like you improve the correlation by at least so much, and the learning rate for that given epoch is chosen in a way that depends on the behavior of the function f. And then once again, like once you get into like the learning phase of the problem, you just temper your learning rate as like 1 over square root t effectively, basically. Yeah. So I guess just to be very clear, like the learning rate schedule and the exploration schedule that you choose does not rely on any particular estimation. Like it's kind of predefined beforehand, and then you like roll this out for a given amount of time and with that particular learning rate schedule. And at the very end of this process, you like have an iterate that satisfies, or like the sequence of iterates that you come up with will have the regret bound that's written over here. Okay, yeah. There's another case, which is what happens where, like maybe another special case, I'll call it, is what happens when the derivative of the function satisfies like a pointwise lower bound. So this is like a kind of the nice case where the derivative is never too close to 0. So you always have some signal that the gradient is giving. And in this case, all you have to do is like change the learning rate schedule in the burn-in period, and you kind of get the same bound that a linear bandit would satisfy. This is like a slightly more general setting than the like a linear bandit or a generalized linear bandit, because there's no upper bound on the derivative. But regardless of that, you can still get the same d square root t regret upper bound. Okay, yeah. I realize that I'm like maybe getting close to running out of time. So what I'm going to do is maybe spend 2 more minutes talking about like how do you come up with these bounds, and then I will skip the section on lower bounds and like maybe I'm assuming that we're going to end soon, so I'm going to skip the section on the lower bounds and just talk about some of the implications, which I think are kind of cool. Okay, so in fact, maybe let's just do that. I think. Yeah, like I would like to talk about that part a little bit more. So in case anyone is curious about this, I'm happy to like talk about this offline. We can come back and talk about this. But yeah, maybe I'll like skip to the last part of this talk. Yeah. Okay, there's a lot of slides. Okay, cool. Yeah. So discussion and further questions. Okay, so I guess one thing that I alluded to earlier is like maybe when you like think about running or using the Eluder UCB algorithm, and like you look at the bound that it gives you for the case of like f of x is equal to x to the p, so the polynomial case, you see that there's like some suboptimality in the bound. Like it tells you a burn-in cost that scales as like d to the p plus 1, when you know that the optimal bound is like d to the p. And so you can always ask, is this like a feature of the or like is it a bug with the algorithm or is it a bug with the analysis? And it will turn out that this is actually an issue with the algorithm. And so the algorithm is basically suboptimal for general ridge functions. And so I'll tell you a statement which is true. And just to be clear, what is LUD UCB? Like you kind of, I'm sure everyone here is sort of familiar with this already, but yeah, you construct a confidence set, which like is going to contain theta star with high probability based on the observations that you've made so far. And then this kind of shrinks over time as you get more observations, and you just play optimistically with respect to like the action A and the theta in this confidence set. And so a lower bound that you can establish for this particular algorithm is for every function f, there is an instance where to achieve sublinear regret, so this is basically a bound on the length of the burn-in phase, the scales is like d over f of 1 over square root d the whole square. So just to be like this is a bound that applies for every single function f. So in particular, like if you like plug in x to the p, or here where p is equal to 3, so x to the 3, and you evaluate this bound, it turns out that this will like require d to the 4 sort of like time or samples to arrive to like the sublinear regret phase. But from what we discussed earlier, the optimal turns out to be d cubed. So there's like some suboptimality in like in the algorithm itself. Okay. You can also establish suboptimality of DEC, or like in general, like any online regression based algorithm, Oracle based algorithm. So just to be clear, like what is an online regression Oracle based algorithm? So what you do is, like for any, you assume access to an online regression Oracle, which is some subroutine that takes in any adversarial sequence of actions AT, and it outputs a theta hat T such that, some like regression like guarantee is true. And the right hand side is like a sort of a function of the family of f's that you are like it's parameterized by the family of functions f that you're optimizing over. And in this case, like maybe for like many classes of f, like you can show that this is just going to be O of d. Right. And so the sort of algorithms that we'll consider in the sense of this lower bound, you assume that you only like the learner only observes like, so there's an online regression oracle that like ingests the actions that were played so far, as well as the rewards that were seen so far, and it like constructs a theta hat t that satisfies this guarantee. And in this model, all you assume is that the learner gets to see these estimates theta hat 1 through theta hat t, but it does not see the rewards itself. And like the learner then has to use these observations to determine what the next action is to play. And so like many algorithms in the literature, including DEC, it's like they satisfy this property that they fall in this particular framework. And so like a theorem that you can establish is for every sort of like, I guess we can think about this as being algorithm that falls within this oracle model. For every such algorithm that falls in this model, and for every f, there's basically like a sort of tie-breaking rule that achieves like that shows you that for that particular algorithm, there's like again the same kind of lower bound on the burn-in cost, which is like d over f of square root 1 over d the whole square. And again, this is kind of suboptimal. Like I said earlier, like for f of x is equal to x cubed, this gives you an extra d factor. In general, for any x to the p, it's going to give you an extra d factor. Right. Yeah. And okay, also, an addendum is this holds for like an offline regression oracle-based learner as well, where the oracle that you assume is like slightly different, but the same lower bound is applied over there as well. Okay, yeah. And one more cool feature is what happens with infinite actions versus finite actions. And so, this is maybe like something that you'll study if you're like, in an intro bandit class. And so like maybe for linear bandits, what we do know is fewer actions lead to smaller regret. And so basically like, the min-max regret decreases from d square root t to square root dt log k if you still have the linearity assumption, but this action space is only of size k. And the intuition is that like UCB needs to construct fewer confidence intervals. So you don't pay for another union bound on the action space itself for in terms of like the number of actions you're union bounding the confidence intervals over. And so you can ask again, is this like a phenomena that's special to linear bandits, or does this hold for nonlinear bandits as well? And it's a very curious phenomena that happens, which is for every link function f, basically there is like a k-armed ridge bandit problem where achieving sublinear regret requires like min of k comma 1 over f of 1 over square root d the whole square sample. So like this is again the bound on the burn-in phase. And for what this is actually saying is for like f of x is equal to x cubed, the fixed cost for the finite action problem where like k is only scales polynomially in d. So here the log k would be like something that scales as log d. For a function like f of x equal to x cubed, whether you have like polynomially many actions or you have like essentially exponentially many actions, you have the whole unit ball as your action space, the like burn-in cost effectively is the same. So there's no benefit that you can get from having fewer actions. And you don't see the same phenomena, which is like UCB needs to construct fewer confidence intervals. And like this is not a feature that holds more broadly outside of like the linear bandit setting. Yeah, there's a question.
Yeah, so I was going to ask for the linear bandit setting, I guess what we're considering in a way is the asymptotic regret, in the sense that we could have a plus d to the 100. We don't, but we could have a plus d to the 100 in that regret. So is it really comparing the same quantity when we say that we don't have this effect?
Good question. It will turn out that okay, so that's a very good question. Yeah, I think it turns out that it will be the same. And the way to witness that is okay, so like the setting over here is like where you assume that the theta belongs to the surface of the unit sphere. If you like change this so that theta lies in the interior of the so it lies in the unit ball basically, all these like lower bounds can also be lifted to like essentially like regret lower bounds. And so this will show you something kind of like very similar to whatever you see over here, like this the square root dt log k. You can like lift the lower bound that I'm telling to one that applies on the regret as well. So as stated, they do not, but like you can do some extra work to like show that they are related to each other. Yes. Yeah, and okay, I guess just to add one more thing, this like is a feature of like being able to choose theta as being very small. Will make the kind of like the burn-in phase very long, because if theta is very small, then the f of theta inner product A is also going to be very small. So like you're just going to be paying linear regret for a very long time. But because you've scaled theta down to be very small, like what it means to pay maximum, like the maximum regret you pay in every step is going to be smaller. So like these two, there's a tension between these two things, and like you can kind of trade this off by choosing theta as like the norm to be of the right scale, basically, of theta, and like it'll give you a bound that applies on the regret as well. Okay. Yep. Okay, so yeah, there are some like follow-up questions, which are what happens. There's like a gap between the upper and lower bounds in the very first thing that I presented. There's like a, the upper bound depends on the derivatives of the function f, and the lower bound depends on the actual values of the function f itself. So how do we like address this gap? And I think this is actually like, from a technical point of view, it's a very interesting question, because so I didn't talk about this in my talk, but the lower bounds already require like coming up with some new techniques to kind of like show something that applies for many length functions. And those techniques have like been applied to their limit effectively for this problem. So we need some new techniques to kind of like fill in this gap, and some new potentially some new notions of information as well. Another good question is like, what happens? So I presented some lower bounds on like Eluder UCB and like offline regression based or like online regression oracle based algorithms. What happens when you like use information directed sampling? And it's not very clear anymore, like whether there's like it achieves the upper bound or it does not achieve the upper bound. And so it's a very interesting question again to analyze the trajectory of IDS. There's also the natural question of like analyzing interactive SGD in like broader settings when like can we like solve this problem where you can choose the sigma t schedule carefully? Like can you do something where you can actually be adaptive to the best derivative that you've seen so far, rather than just the derivative around the current point that you are at? And also like extensions to multi-index models. Yeah, and just in terms of like the take-home message, basically there could be a phase transition in the regret of nonlinear banded problems depending on the link function f, and it requires maybe rethinking like what we would call as like the class of algorithms you think about implementing for the problem at hand, and sometimes you might have to look at other natural algorithms like SGD. And new notions of information may be required to get lower bounds. I didn't talk about this today, unfortunately, because of time. But this is again like something that that would be very interesting to study in more detail. Right, and also like finite action settings like appear to have different behavior between linear and nonlinear bandits. Yep, and with that, I'll end today and just put a link to so like most of the results that I presented today, except the stuff on SGD, is in the paper that's linked over here. And the results on SGD are not out on arXiv yet, but hopefully they will be very soon. So and I'll try to see if I can share that with everyone once the paper is out on arXiv then. But yeah, with that, thank you very much for your attention, and also for all the nice questions. And feel free to reach out to me by my email is over here in case you have any thoughts afterwards.
Cool.
Thank you.
Great. Thank you for the talk.
Thank you very much. Yeah.
We can see if there are some questions now. Otherwise, if people prefer to ask some question offline, we can stop the recording and having a more informal discussion. But let's see first if someone has a question to ask.
I have a quick question. So I was wondering so I've been thinking about some problems in the sort of RL plus LLM space, which is kind of also high dimensional. I was wondering if some of this burn-in period kind of thing might disappear if you don't have this uniform prior that you have imposed and have like a more warm start instead of starting uniformly. What do you think about that?
I guess it probably depends a lot on the particular problem that you're talking about. So I can imagine like something like this happening for certain kinds of link functions. But like generically, like, for instance, if you're initialized at a point where you already have constant correlation with theta star, then you're already initialized in like the learning regime. And so you don't have to pay this burden cost anymore. You only just pay this d square root d bound. But yeah, there are like many sort of there are probably many interesting cases in between where you don't have constant correlation, but you kind of still have some like a stronger prior on where theta star is, for instance. And yeah, I'll just say that it probably depends a lot on the function itself. Yes. Yeah, like for I mean, I guess like what's the specific context you kind of like are studying?
Yeah, I don't know if we have enough time for
Okay,
for
that's fine.
the
That's
discussion.
fine.
But I can definitely reach out to you offline.
Well, if we want to, we can stop recording and then just carry on with
Oh
discussion.
yeah, that would be cool.
Yeah, let's do that. So let me stop the recording.